This video demonstrates the use of Optum G2 for slope stability analysis. It also covers some of the differences between limit equilibrium and limit analysis. Optum G2 is based on limit analysis. The slope we'll consider is shown here. It's a slope of a homogeneous material, a more Coulomb material, with parameters shown here. C cohesion of 41.65 kPa, friction angle of 15 degrees, and a unit weight of 18.82 kilonewton per square meters. It has a height of 20 meters and a slope of 213. Now, with limit equilibrium, which is a popular method for slope stability analysis, the way it typically works is that you first postulate a mechanism of collapse defined by some slip surface or slip line as shown here. It may be circular, it may be non-circular. And then what you usually do is you calculate the forces that tend to induce instability, and you calculate the forces that tend to resist it. And once you have these two sets of forces, you can work out your factor of safety. Now, depending on exactly what method you use, these forces are calculated in slightly different ways. And there's a lot of methods around. I would say something like probably 10 to 15 different methods, which each are based on reasonable assumptions and reasonable approximations, but at the end of the day, once the results are in, give one result or another. Here are some of the methods, or 8 of the methods that are all quite popular and currently in use. Some of them involve circular slip surfaces, some of them involve non-circular slip surfaces. And for this quite simple slope of a homogeneous material, we have a range in the factor of safety from about 1.25 up to about 1.45. If you look at it graphically, it looks something as shown here. So the question, of course, is which, if any, of these solutions is the correct one, because there can only be one correct solution to this problem. Everything is known, the geometry is fixed, the material parameters are fixed, we know there are certain conditions we should satisfy, equilibrium, we shouldn't exceed the strength of the material, and so forth. So there can only really be one solution, and what is that solution? And this is where limit analysis comes in. So let's switch to Optum G2 and let's first define the geometry, and I'll do that by direct coordinate input. The coordinates were shown in the slide before, and I will enter those. And here we go, and the geometry is done. I'll then apply a material, and I'll apply the basic MC material. It's a basic, more Coulomb material, and I'll modify the parameters to match what we have for this particular problem. Friction angle of 15 and the unit weight here 18.82. I will apply standard fixities as supports here, here, and here. And then I'll go to the stage manager, and as analysis types I'll choose strength reduction. What we want to do in this analysis is we want to reduce the material parameters to cause collapse, and in that way, with the actual parameters and with the reduced parameters, we can work out the factor of safety, or the factor of safety will be calculated automatically. I'll use 1,000 lower bound elements, and I'll also use mesh adaptivity for this stage here. I'll then clone this stage, and then I have a second stage where I'll have element type upper. So I now have two identical stages, except in the first stage I have element type lower, so I calculate lower bounds, so let's call that LB, and then in the second one with element type upper, I will get upper bounds. And let's run the analysis. Let's set it running. And strength reduction analysis works via a sequence of iterations where you gradually hone in on the reduction factor necessary to cause collapse, and that reduction factor is exactly the factor of safety that we're after. So it's done now, and for the first stage, the lower bound stage, well, we have a reduction factor, a factor of safety of 1.392, and in the second stage we have a factor of 1.417. Look at the collapse. You can see the elements, the mesh has been adapted to basically capture the solution in the best possible way. If you look at some of the plastic strains, say, you see that these define a slip surface very similar actually to the one I showed you before, except this slip surface is of course not defined beforehand. It comes out as a result of the calculations, and the slope eventually collapses like this. If we go back to the presentation and have a look at how these results fit with the limit equilibrium results, we see that here. So here are the upper and lower bounds, and we know that the true solution is somewhere in between, so we have a relatively narrow gap in this case, and that is the case for most problems, and gap of about 1 to 2% or something like that, and we can take the average, and then we have a really good estimate of what the correct solution is, and we have even a worst case error over here, which in this case is less than 1%. And we see as well that some of the limit equilibrium solutions are actually quite accurate. The only problem is that you don't know which are the good methods and which are the bad methods. It sort of depends on the problem, and this range is not uncommon, so there's a bit of a problem. Whereas with limit analysis, you get these rigorous upper and lower bounds, and you know the true solution is always somewhere in between. As a final demonstration, I just wanted to show that suppose that we have a thin layer of a weak material down here close to the toe of the slope. So a thin layer, in this case it's 1 meter, so it's not that thin, of a weak material, and I'll apply another material to this layer. I'll use the soft clay. MC is one of the other default materials in Optum, and I'll modify the parameters. I'll say I have a C of 10 and I have a friction angle of 15, as in the original material. I have the same unit weight, and so basically I've reduced the cohesion from the 41.65 down to 10. Everything else is the same. And let's have an upper bound stage as well, and let's see what kind of results we get from that modification. So first the lower bounds, and I can already see now they're definitely below the lower bounds we had before, and the upper bounds will sort of display the same trend. So this weak material will really have an influence, and here are the results. The lower bound 1.20 and the upper bound 1.25, 2425, something like that. So a good estimate, 1.22 plus minus 0.02. Again, a fairly good accuracy, or very good accuracy, I should say. And here you see the slip line. It looks much as before for the upper part of the surface. We have this slip line extending from the top of the surface, from the top of the slope and downwards, but then once it hits the weak layer, well, it slips along this weak layer, and it slips something like that. So that demonstrates slope stability analysis in Optum G2. Optum G2 is a general purpose program. It's of course applicable to many other types of problems, but it is a very convenient for slope stability analysis as well. You can download the program from our webpage, OptumG2.com, where you'll also find other material, videos, manuals, and so forth.